Hey there, and welcome. We're surrounded by these incredible feats of science and engineering that we just completely take for granted. So today, we're going to unravel the hidden physics in something you're using right this second: your clothes.
Seriously, just take a look at the shirt you're wearing, or a sweater, or even your jeans. Did you ever stop and wonder what gives that fabric its strength? Like, why doesn't it all just fall apart into a pile of fluff? Well, the answer is a total masterpiece of simple, elegant physics.
It really all comes down to one single fundamental action. It's not about the material itself, not really, but how that material is put together. The big secret to turning all those flimsy little fibers into a strong, durable thread is actually pretty simple. It's the twist. Yeah, the official definition calls it the spiral disposition of the components, which sounds a little scientific. But in plain English, it just means twisting loose fibers together in a spiral. That's it. This simple action creates friction and tension, and that's what locks them all together into one strong unit. Without this twist, your t-shirt would literally be nothing but lint. Now, this isn't just some random spinning. The direction of this spiral is a really deliberate choice in textile engineering. There are only two fundamental ways to twist a thread, and once you know what you're looking for, I promise you are going to start seeing them absolutely everywhere. They're called S-twist and Z-twist, and the names are just brilliantly simple. They literally come from the visual direction the fibers take, which just happens to mimic the slant of the letters S and Z. Let's break that down. Okay, so look closely at this. If you hold a thread straight up and down, and the spirals seem to go up and to the left, just like the middle part of the letter S, well, that's an S-twist. And if they go up and to the right, like the middle of a Z, you've got a Z-twist. It's that simple, and it's a fundamental building block of every single fabric you have ever touched. So how in the world do scientists actually study this? They don't just guess, right? No, they create a perfect blueprint to understand exactly what's happening deep inside a piece of yarn. They built what's known as an idealized model. Just think of it like a perfect, simplified version of a real-world object. It's designed to ignore all the messy, random little imperfections of reality so that we can focus on the core principles and the beautiful geometry underneath it all. So, this blueprint, it follows a few simple rules. First, you imagine the yarn as a set of perfect cylinders, one tucked inside the other. Then, each fiber follows a perfect spiral path, that's a helix, around one of those cylinders. It creates this amazing sense of order. A fiber never, ever wanders from its path, and the one right in the dead center, it stays perfectly straight. It's all about perfect geometric order. Okay, let's make that even simpler. Just picture a perfect cylinder in your mind. Now imagine wrapping a line around it at a constant angle. That beautiful spiral you're seeing? That's a helix. And that is the exact path every single off-center fiber takes in this perfect model of yarn. Okay, so we've got this kind of complex 3D spiral. How could we possibly describe that with simple math? Well, this is where scientists came up with an incredibly clever trick. What if you could just, unroll it? And bam! This is the magic moment. When you unroll that cylinder and lay it flat, that complex 3D spiral path suddenly becomes a simple, straight line. It's the hypotenuse of a right-angled triangle. And just like that, we can use basic high school geometry to describe the entire structure. It's genius. This little geometric insight is the key that unlocks absolutely everything. So let's see how this one simple trick allows us to capture the physics of yarn in a single, really elegant piece of mathematics. Because we can now represent that twist with a simple triangle, the whole complex relationship between the yarn's size, its twist, and the angle of the fibers can all be captured in a single beautiful formula. And here it is. Now, don't let the symbols scare you. It's actually pretty straightforward. The tangent of alpha, which is just the angle of the fibers on the surface, is equal to 2 times pi times r, the yarn's radius, times t, the amount of twist. This one equation beautifully connects the yarn's thickness, how tightly it's twisted, and the final angle of the fibers. It's the whole blueprint in one line. But, of course, the real world is always a little bit messier, right? As the source material points out, this perfect model doesn't apply exactly to real yarn. Real fibers just aren't perfect. But this idealized model gives us an incredibly powerful starting point for understanding the much, much more complex reality. All right, so we've gone from a sweater all the way down to a geometric blueprint and a mathematical formula. So what? How does all this theory actually affect the clothes that we wear every day?
Well, there's a very real, very physical consequence to all of this twisting. Just think about it for a second. A spiral path between 2 points is always going to be longer than a straight line, right? So when you twist fibers, the overall length of the yarn actually has to get shorter. It contracts.
And there are even two different terms for this. For yarn that's made of short, staple fibers like cotton, it's called contraction. But for yarn made from a single, continuous strand, like silk or polyester, it's called retraction. It's the same basic principle, just a different starting material. And listen, this is not just some fun fact for a textbook. This shrinkage is an absolutely critical factor in manufacturing. If you don't account for it, every single piece of yarn you produce is going to be the wrong size. This slide just shows how ridiculously precise the whole manufacturing process has to be. The source gives a perfect example. Let's say you want to make yarn with a final fineness, or count, of exactly 18. Well, if you know it's going to contract by 5% during twisting, you can't aim for 18. You have to start with a count of 18.90, so that after it shrinks, it lands exactly where you need it to be. I mean, this is applied physics right there on the factory floor. So the huge takeaway from all of this is that this simple little thread holding your shirt together is anything but simple. It is a precisely engineered structure, constantly balancing tension, friction, and geometry, all to create strength from what started as weakness. And that's really our final thought for you today. The next time you pull on a sweater or a pair of jeans, maybe take a closer look. Are you just going to see fabric, or are you now going to see the thousands of tiny twisted helices, an everyday masterpiece of physics? Thanks so much for watching.